Hi, AP Statistics. It's just fun. Hi, AP Statistics class. If if 2020 wasn't enough, we have power outages in San Diego County today, so just roll with it. So today, which is Thursday, December 2nd, when I'm recording this video, early in the morning, I'm going to do a couple review questions about random variables and probability. So on this first page of the notes, we'll look at some random variable questions. And on the second page of the notes, which will probably be a second video, I don't know yet, can't predict the future. I don't even know. Are we going to have water tomorrow? We don't have electricity today. But yeah, let's just start reviewing. Consider a company that manufactures and ships small stereo systems. The times required to pack the stereos can be described by a normal model with a mean of 9. It's important stuff. Mean of 9, standard deviation of 1.5. The times for the boxing stage is also normal with a mean of 6 and a standard deviation of 1. What is the probability that packing 2 consecutive systems takes over 20 minutes? Now we're asked for a probability and we're told that these are normal models. I hope that registers in your brain that like, hey, we're probably going to be using a normal model here, normal CDF command. This first question is asking about packing 2 consecutive systems and it takes over 20 minutes. That's going to be our boundary of our normal model. And we're only interested in the packing information, which I've highlighted in green. Part B says packing versus boxing. So in part B, we're going to have to compare the two, but in part A, we're just talking about packing 2. So let's let P be our random variable, and that's the time to pack. And we'll let B be our random variable, time to box. These are continuous random variables. Since time, you can have a bunch of different times on an interval. There aren't gaps in between times. 1 minute and 2 minute, there are gaps, but you can get down to the second and millisecond and nanosecond and stuff like that. So these are continuous random variables. And as a continuous random variable, that will help us and allow us to use a normal model, since a normal model is a continuous model. So we want to pack 2 consecutive systems. Well, for a normal model, we need the mean and we need the standard deviation. We already have the shape. We're told that it's normal. So we want the mean of packing 2 systems. So we'll do the time to pack the first plus the time to pack the second. So that mean would be, well, whatever the mean it is to pack the first plus whatever the mean it is to pack the second. Kind of has a sing-song to it. So if it's 9 minutes to pack and you have another one that's 9 minutes to pack, I hope it's not too mind-blowing to think if there are 2 that you're packing, it's going to take about 18 minutes on average to pack 2. Sometimes students will want to divide that by 2, but then that would be only taking 4.5 minutes to pack on average. You have 2 of them that you have to pack. I don't know how many hands you have, but you take 9 minutes to pack 1, so it's probably going to take 18 minutes to pack 2. Now let's find the standard deviation to pack 2. Now, this is where it really comes down to it. Do you remember how to combine standard deviations of random variables? Sadly, it is not this. I say sadly because a lot of students want to do that, but we don't add standard deviations of random variables. We have to use the Pythagorean theorem of stats. The Pythagorean theorem of stats is that the variances add, but the standard deviations don't. Or in other words, we have to square these. And then typically, rather than squaring that first term, usually just end up square rooting this. So we get that. So this would be, we're told it is 1.5 minutes to pack. So this would be the square root of 1.5 squared plus 1.5 squared, which equals 2.12. Okay, so we have our standard deviation. We have, standard deviation, and we have our mean. And the units on both are minutes. So on our normal curve, definitely want to sketch a graph of the normal curve. We can plot our mean as 18, our standard deviation as 2.12, and our boundary is 20. It looks like it's a little less than 1 standard deviation to the right of the mean, and we can shade to the right of that since we want over 20 minutes. We're looking for the probability that p plus p is greater than 20. Maybe I shouldn't have used p because that's a lot of p's. The first p is probability, and then the other p's are my time to pack random variable. Now, I like finding z-scores. I want to review that with you. I don't want you to forget the z-score formula. The z-score formula is your boundary minus your mean over your standard deviation. So we could rewrite this probability as, what's the probability that our z-score is greater than 0.943. I like to review z-scores. You can see those on the AP exam, and something that we'll do later in the class. You'll have z-scores quite a bit, so I don't want you to forget that formula. But probably what you'll do is you'll do normal CDF, lower bound, upper bound, mean, and standard deviation. And you'll probably use the units rather than the standardized units. Lower bound's 20, upper bound's some large number, the mean is 18, and the standard deviation is 2.1. So we get an answer, 0.173. So what's the probability it takes over 20 minutes? That's about 17% chance. So if there's a quality control or a manager around, and it's like, hey, Johnny, why are you taking so long for? It took you 20 minutes to pack those 2 consecutive systems. Well, Johnny could say, well, sir, it's about 17% of the time you would expect that it would take over 20 minutes. I don't know if you should be that concerned. 17% isn't that surprising of a probability. All right, so that's the first question. The next question, we have, what percentage of stereo systems take longer to pack than to box? So we would like the packing time to take longer than the boxing time. I don't really like that I'm using red here because I typically don't use red at this point. So let me fix that. Packing takes longer than boxing, and we want the probability that packing takes longer than boxing. We could also write this as, if I subtract b from both sides, packing minus boxing is greater than 0. And that's really helpful because that shows us our boundary. So let's find the mean of p minus b and the standard deviation of p minus b. I'd encourage you to pause the video, see if you can figure those out. Packing time is 9 minutes. Boxing time, subtracting here. We're going to be doing the mean that it takes to pack minus the mean it takes to box. Packing is 9 minutes. Boxing is highlighted in yellow, 6 minutes. So on average, it takes 3 minutes longer to pack than to box. The standard deviation, we would have the variance to pack plus the variance to box. Remember, the Pythagorean theorem always has a plus in between there. Even when you're subtracting, you have increased variability, not decreased, so we add and square root that. So we would have the square root of 1.5 squared plus 1 squared. So we get 1.8 minutes. And then we can make our normal curve. You have a mean of 3, a standard deviation of 1.8. And we just need a boundary. And the boundary is, because we wrote it like this with a 0, somewhere maybe over here is a 0. And we want greater than 0, so that will shade to the right of 0. And in my honor, we'll find a z-score. The z-score would be 0 minus the mean over the standard deviation, which is -3 divided by 1.8, -1.67. To find the probability, we would do normal CDF. Make sure you label your parameters. The lower bound is 0, the upper bound is some large number, the mean is 3, and the standard deviation is 1.8. And we get an answer of 0.95. So it's very likely. And I'm just looking at the numbers. Like we said before, it's 3 minutes on average. It takes longer to pack than the box, typically. So if you're asked what's the probability or percentage of stereo systems that take longer to pack than a box, typically it will take longer to pack than a box. So this high percentage kind of makes sense in the context that we would have the majority of stereo systems, 95% of them, take longer to pack than a box. What assumption did we make to answer this question, and is this a safe assumption? We assumed packing and boxing are independent. The Pythagorean theorem of statistics requires that random variables are independent. Just like in the Pythagorean theorem of geometry, we require that the triangle is a right triangle. This Pythagorean theorem of statistics has a similar condition. The random variables have to be independent. So, for instance, maybe a crew works slower, so the packing and boxing times may not be independent. Or maybe it's like a night shift or something. Or maybe it's a really bad worker. Maybe Johnny, that we mentioned earlier, maybe he doesn't do a very good job. So maybe whenever he's working, packing time goes down and boxing time goes down. Or like if you have to package it or pack it before you box it, if there's a delay in packing, then there's going to be a delay in boxing. So they are not independent of each other. So it may not be, maybe not, a safe assumption. We'll call that good for this first page. In the next video, we'll look at the next question, which is a previously released AP question. And I will share my video right there, right over the z-score. So I can where is it? So I can touch the z-score right there. If you made it this far in the video, give me a thumbs up. Thanks for watching all the way to the end, because you're committed. See you later.